In our last lecture, we outlined a 7-step procedure for sketching the magnitude-frequency response plot from the transfer function. In this lecture, we'll look at a large number of example problems to illustrate how the method can be used. Let's now try applying these rules to a simple example problem. And the example problem we'll look at is a simple first-order system. The transfer function of interest is g of s equals 15 over s plus 3. In step 1, we find the integer m, which is the number of zeros at the origin minus the number of poles at the origin. For this transfer function, the number of zeros at the origin and the number of poles at the origin are both 0. So m is 0 minus 0, or 0. In step 2, we remove from the transfer function any poles or zeros at the origin to find a new transfer function, which we call h of s. And then we find the value of this at 0. Now, since g of s has no poles or zeros at the origin, h of s is equal to g of s. Then when we evaluate h of s at s equals 0, we find the value 5. We take the absolute value of this number and we plot it at 1 radian per second. In step 3, we draw a line through the point we just plotted, and this line will have slope m, where m is the integer that we found in step 1. So for this transfer function, m was equal to 0, and we draw a line with 0 slope through the point we just found. This is our low-frequency asymptote. In step 4, we determine the poles and zeros of the transfer function h of s, and then we order them by frequency magnitude from lowest frequency to highest frequency. For this particular transfer function, we will have only one pole, and that's at minus 3, and the magnitude of this pole is 3. In step 5, we move from low frequency to high frequency, adjusting the slope of the line we just found. We decrease the slope by 1 for each pole that we encounter, and we increase the slope by 1 for each zero. So now let's apply this to our example problem. We had only one pole at the magnitude 3 radians per second, so we'll decrease the slope from 0 slope to minus 1 slope at 3 radians per second. Since we have only one pole and no zeros, that means that we're done now with the asymptotic plot. We've accounted for each pole and each zero. So we move on to step 7. Here we'll cut the corner on the asymptotic curve to form the actual curve, at least our approximation of it. And since the pole is on the real axis, we know it'll be a gentle bend here at the corner. So here I'm showing the actual curve in blue and the asymptotic curve in red. We've now completed the construction of the magnitude plot for the transfer function g of s equals 15 over s plus 3. And before moving on, let's note that this transfer function is a low-pass transfer function. It keeps the low frequencies and rejects the high frequencies. Let's now try sketching a slightly more complex transfer function. And this transfer function, example number 2, will have a 0 in it. So we have g of s equals s plus 3 divided by s plus 36. Our first step in construction is to find the integer m, which is the number of zeros at the origin minus the number of poles at the origin. In this case, we have no zeros at the origin and no poles at the origin, so m is equal to 0, just as in example 1. In our next step, we remove any poles and zeros from the transfer function g of s to form a new transfer function h of s. In this case, h of s is the same as g of s, since there's no poles or zeros at the origin. We then find the value h sub 0 by evaluating h of s at s equals 0. In this case, we find h sub 0 as 1/12, and we plot this point at 1 radian per second. In step 3, we draw the low frequency asymptote through the point we just plotted, and this asymptote has a slope of m decade per decade, where m was the value we found in step 1. In our example, m is equal to 0, so we draw a line of slope 0 through the point 1/12 at 1 radian per second. In step 4, we find the magnitude of the frequencies of each of the poles and zeros. And in this case, we have a 0 at -3, and we have a pole at -36. The magnitude of the 0 is 3, and the magnitude of the pole is 36. In step 5, we move from low frequency to high frequency, adjusting the slope of the line at the frequency magnitude of each pole and zero. So in this example, we have a 0 at -3 and a pole at -36. So we first adjust the slope for the 0 at -3. So at 3 radians per second, we increase the slope to +1. Then, at 36 radians per second, we decrease the slope from +1 to 0. We've now completed our adjustments of the slope. We've accounted for all the poles and zeros of h of s. We'll now finish this example by sketching in what the actual frequency response plot looks like on the basis of our asymptotic plot. And in this case, the poles and zeros are on the real axis, so we simply need to cut the corners and smooth out the curve. Here I'm showing the asymptotic and actual frequency response plot for our system G of S. So I hope you're beginning to see that it's easy to generate these magnitude plots for various transfer functions. Now let's look at another example. And in this example, we'll have a pole at the origin. The transfer function for example number 3 is g of s equals s plus 3 divided by s times s plus 36. So you see we have the 0 at -3 and the pole at -36 that we saw in the last example. But we also have a pole at the origin. The inclusion of the pole at the origin will primarily have an influence on our first step. This is where we find the integer m, which is the number of zeros at the origin minus the number of poles at the origin. So now, for this transfer function, we find m is equal to -1. If you recall, in the previous example, m was equal to 0. In step 2, we remove any poles or zeros at the origin to find the new transfer function, h of s. So now, with the pole at the origin removed, h of s is equal to s plus 3 over s plus 36. And this is the same h of s that we found in the last example. When we evaluate h sub 0, it will be the same as well. It is 1/12. So we plot the same point at 1 radian per second that we did in the previous example. We now draw our low frequency asymptote, and this is a line of slope m through the point we just plotted. For this example, m is equal to -1, so we draw a line of slope -1 through the point at 1 radian per second. We now move on to step 4, and in step 4, we organize the poles and zeros of h of s according to their frequency magnitude. So we've got a 0 with a frequency magnitude of 3 and a pole with frequency magnitude equal to 36. In the next step, step 5, we move from low frequency to high frequency, adjusting the slope of the line according to each pole and each zero. The slope decreases for each pole and increases for each zero. In our example, we first encounter a zero at a frequency magnitude of 3, and so here we increase the slope from -1 to 0. The next pole or zero that we encounter as we move up in frequency is the pole at -36, and it has a frequency magnitude of 36. So we will adjust at 36 radians per second the slope again. It will go from 0 to -1. We have now accounted for all the poles and zeros of h of s, and so we've completed the asymptotic frequency response curve. We can now move on to step 7, where we'll try to put in the actual curve on the basis of rounding the corners here for the poles and zeros. So here we have the asymptotic curve as well as the actual curve achieved by rounding the corners. We have now completed example number 3. And before we move on, I just want to point out a simple fact about this particular transfer function. Because of the pole at the origin, the frequency response goes to infinity as the frequency goes to 0. That is, this transfer function has infinite gain at 0 frequency. This is a property that occurs whenever a transfer function has a pole at the origin. We'll now look at example number 4. I've included this example to show you that the low frequency asymptote does not have to cross through the point that we draw in step 2. The transfer function for this example is g of s equals 10s plus 3 over s times s plus 36. And you'll note this looks a lot like our last example. The only difference is the 0 that was at -3 in our last example is now at -0.3. So its frequency magnitude is now 0.3. As before, we can find m is equal to -1. h of s will be 10s plus 3 over s plus 36. And h sub 0 will be 1/12 as before. So we'll sketch a point at the value 1/12 at 1 radian per second, and then we'll draw a line of slope -1 through this point, and this is our low frequency asymptote. Then if we arrange the poles and zeros from lowest frequency magnitude to highest frequency magnitude, we'll find there's a 0 at 0.3 and poles at 36. So at 0.3 radians per second, we increase the slope from -1 to 0. And then at 36 radians per second, we decrease the slope from 0 to -1. That accounts for all the poles and zeros. So now we have constructed the asymptotic frequency response curve. Note that because of the 0 at a frequency lower than 1 radian per second, that the asymptotic curve veers away from the point that we plot in step 2. Now we'll sketch in the actual curve using the asymptotic curve as the backbone. The actual curve is shown here in blue, and you'll note that this curve does not pass through the point that we plotted at 1 radian per second. In our next lecture, we'll examine 4 more example problems.